In this lesson, we're going to learn how to do some calculations involving uniformly accelerated motion. First of all, what is uniformly accelerated motion? It's just a specific type of motion that involves a constant acceleration. So if a car is constantly speeding up at a constant rate, like 3 meters per second squared, that would be a uniform acceleration or uniformly accelerated motion. So essentially that's all it is. It's constant acceleration. Now, let's just put that acceleration. That's essentially all it is. Now, in order to do calculations involving this, we have a calculation or an equation for acceleration, right? And our equation for acceleration looks like this. Average acceleration as a vector is the change in velocity over the change in time. Or sometimes we write it as v2 minus v1 over delta t. The final velocity minus the initial velocity over time. This is a useful equation for calculating when we have constant accelerations, right? Like a car is accelerating. We know the initial velocity, we know the final velocity, we know the time. But what happens if we want to know something else? Like, for example, what if we want to know if a car accelerates at a rate of 3 meters per second squared for 5 seconds, how far is that car going to travel? What's the distance is that car going to travel? And that's a useful calculation as well. Notice how these equations, or this equation, doesn't have displacement in it at all, right? But if you use a little bit of algebra magic, do some substitution into here with some other equations, do some rearranging, you can actually come up with some more equations that do have displacement in it. In fact, there are 5 equations that you can come up with. I'm not going to show you how to prove those equations right now. We'll save that for later. For now, I just want you to know how to use these equations. There's also a very good reason why there are 5 equations. The first equation is actually, if you look very closely, it's actually the same thing as this equation, the equation that we're used to. It's just rearranged. And notice how instead of v2 and v1 for the final and initial velocity, they use vf for final and vi for initial. Just another way of saying it. Both of them are correct. But if you rearrange this equation here with the a, you can actually get this. If you solve for final vf or v2, you can actually get this equation. So that first one is actually just the equation we're used to, just shown in a little bit of a different form. So you can actually use this equation in place of this one. The other equations are just, as I said, they're just, you get them with a little bit of substitution and stuff like that. But the reason why there's 5 of them is because there are 5 variables that are important to us here. Those 5 variables are vf, vi, so the initial velocity, the final velocity, the acceleration, the time, so that's 1, 2, 3, 4, and lastly, the displacement, right? So that's a total of 5 variables. And if you look at each one of these equations, each one of these equations has 4 of those variables, and it's missing one of them. So for example, that first equation that we're used to using is missing. I'm just going to make a column here on the side, so for what it's missing. This first one is missing delta d, right? There's no delta d in it. So if we're not worried about delta d, we're not worried about the displacement, we don't need to use that first equation. The second equation doesn't have time in it. So if we're given a question and it gives you the final velocity, the initial velocity, the acceleration, the displacement, but it doesn't give you the time, you can use that equation to solve for whatever unknown you want, right? The third one, if you look closely, it's missing the acceleration. So it's based on the fact that we're undergoing an average acceleration, but if you don't actually know the acceleration, you can use this formula, right? It uses the final velocity, the initial velocity, the time, and the displacement. The next one, if you look closely, it's missing the final velocity. So if you know the starting velocity, but you don't know the final velocity, instead of calculating that second velocity, which can be a bit of a pain, we can use that equation. And this last equation is very similar to that fourth one, and it's just missing the initial velocity, right? So if we know the final velocity, but we don't know the initial velocity, we can use that equation. All right? So let's see how we can actually use these equations to solve a problem. First question, down here, example problem 1. A car starts from rest and accelerates uniformly over a time of 5.21 seconds for a distance of 110 meters. Determine the acceleration of the car. You might be tempted to use this equation, our standard equation for acceleration, But notice how in this question we're actually given the distance, right? 110 meters that the car accelerates for. And nowhere in this equation is distance, so we can't really use that equation as it is. Now, before starting here, let's a good way to start this, just so you sort of are keeping track of everything, is to make note of what we're given in the question. So I'm going to start off with this. What are we given? So just looking at the sort of the numbers in the question, we're given that 5.21 seconds. So this acceleration happens for 5.21 seconds. So that's going to be our delta t, right? 5.21 seconds. We know the distance, so delta d is 110 meters. Now, I know it's a vector technically, but this question, we're going to all assume it's in one direction. So we're not going to worry too much about the direction. Also, the question doesn't give us a direction, so we're going to assume forwards. The positive direction is forwards here. What else are we given in this question? There's no other numbers, but if you read very carefully, you might see that we are given a little bit more information. That's the car starts from a rest. So rest, if it starts from rest, we would say the initial velocity is 0, right? It starts from rest. The next thing is so those are the three things we're essentially given in the question. What do we need to find in this question? What do we need to solve for? And the answer there is the acceleration. It tells you right there. We're looking for the acceleration, right? That's the unknown. So the next step here, once we have that, is to essentially solve the problem. But in order to solve the problem, we need to know what equation to use. So let's go back up here. Notice how this question is concerned with time, distance, initial velocity, and acceleration. Those are sort of the four things we need for this question. Notice how there's something missing, and that's final velocity. So we don't actually know the final velocity of the car, and we don't really care about the final velocity of the car. So if we look at which equation doesn't have final velocity, you'll notice it's this fourth one here, right? So that's the equation we're gonna use. So I'm gonna leave it there at the top of the screen so we can see it still. So delta D equals VI delta T plus 1/2 A delta T squared. So in order to do this, let's first rearrange this equation for average acceleration, right? That's what we want to find. So let's rearrange it and then plug in our numbers. So to rearrange it, I'm just going to actually highlight this. So A is the thing we're trying to solve for essentially. So to rearrange it, I'm going to bring this V1 delta. Actually, no, even easier. V1 is 0, right? Or V naught, V initial is 0. So let's just, before we actually rearrange it, that whole thing's going to go to 0 because V1 times delta T is just going to be 0, right? Because V1 is 0. So that actually makes the equation a lot easier to deal with. And well, I'll rewrite it out here just for ease of calculation. A delta T squared, right? So now again, we're trying to solve for A. So what can we do? Well, we can divide both sides by delta T squared, right? And that's going to cancel out with that. And then in order to get rid of the 1/2, we can divide by 1/2. Dividing by 1/2 is actually the same thing as just multiplying by 2, right? So that's going to get rid of that. So essentially we can say A, our average acceleration, is equal to 2 delta D over delta T squared. Now that we have that, it's going to be pretty easy to just plug in our values that we know to come out with the answer. So our acceleration is going to be 2 times 110 meters over delta T squared. And delta T is 5.21 seconds squared. So if you plug this into your calculator, you should get the final acceleration, really it's the average acceleration, is 8.10. And if we look at the units here, it's going to be meters, and then the seconds are squared, so meters per second squared, which is what we would expect if it was an acceleration. So that's the answer. And I'm just looking at significant digits here. Let's just double check that we did that okay. It looks like the significant digits in our question are 3 significant digits here and probably 3 significant digits here. So it makes sense that our final answer is in 3 significant digits. So the average acceleration is 8.1 meters per second squared. One thing to keep in mind when doing these questions, since we're working in the metric system, it's always good to sort of stick with our base units, right? Meters and seconds. So it'll just basically, if you use that, you're always going to come out to a simple answer, which is going to be the correct units. So essentially just for everything, stick to meters and seconds. So convert anything that's not in meters and seconds to that before doing these calculations. Okay, so for the second question, I encourage you to try it yourself. Pause the video here, try it yourself. And when you think you've got an answer or you're stuck, you can unpause and see what's going on. So again, in this question, we're going to start off with given. What are we given? Well, first of all, we're given that it accelerates from 18.5 to 46.1. That means our VI, our initial speed, is 18.5 meters per second, and our final speed, VF, is 46.1 meters per second. And this takes 2.47 seconds, so that's our delta t. We need to actually find two things in this question. We need to find the acceleration and the delta d, the distance, right? Those are the two things we need to find in this question. We can do those two things separately, obviously. So let's start off with finding the acceleration. So if we're looking for the acceleration, let's look at our equations. We have VI, VF, delta t, and acceleration. Those are our four things that are useful. Now, if you're paying attention, you can realize that's basically our regular acceleration formula. We can use that one. We can also use this one, right? Because we don't care about the displacement in this question. We can also use this equation, but this one is already solved in terms of acceleration, so we don't need to do any rearranging. So we might as well just use that equation, right? So that our acceleration, this is the solution. This is how we solve it. The acceleration is just going to equal V2 minus V1 over delta t, or V final minus VF. Actually, you know what? I should be consistent in the question, because in the given I put VF and VI, so in the solution I should put VF and VI. So VF minus VI over delta t, right? And our final, so just going over here for a second, our final is 46.1 meters per second minus 18.5 meters per second, all over 2.47 seconds. So our acceleration comes out to, with three significant figures, 11.2 meters per second squared. If we look at our units here, we essentially have meters per second. The top is just going to be meters per second, right? Because we're subtracting 2 meters per second, divided by seconds. So that's just meters per second, or meters per second squared. So that is our acceleration. Not too bad. Now let's find our delta d. So if we look back at these equations, we might need to use another equation here because that equation doesn't have delta d in it. And really, the thing to keep in mind here is we actually know four things now, right? We know the VI, the initial velocity, we know the final velocity, we know the delta t, we also know the acceleration. So we can actually technically use any of these equations, and solve for delta d, right? Because we know four of the things, we just need to find the fifth one. Now, because this is a calculated number, we rounded this, it's going to be a little bit less accurate. So let's use one that doesn't involve this number. Let's try to stick to these three still. So which one of these three, which one of the equations uses these three and delta d? Well, it's going to be this one, right? The one that doesn't include average acceleration. And now that I'm looking at this, I actually see there's a mistake here. This equation right here should be, let me make sure I have the right color pen, should be VF plus VI over 2. It's actually just the average of the two velocities times the time. So sorry about that. Please correct that on there. But that is the equation we're going to use. So delta D equals VF plus VI over 2 times delta T. And if we plug in our numbers, so we know our final velocity is what, 46.1 meters per second plus 18.5 meters per second over 2 times delta t, which is 2.47 seconds. I'll put that in brackets as well. So if we do that calculation, we actually get 79.78. And what are our units? We'd expect it to be meters because it's a distance, but let's just double check with our units here. We have meters per second and meters per second, right? Meters per second and meters per second. And then we're multiplying by seconds. So the meters per second, these per seconds, are going to cancel out with that second, and we're going to be left with meters. Perfect. So that should be the answer, meters. Also looking at significant digits, delta D. Looking at significant digits, the question seems to have 3 significant digits for each. So our final answer should also be 3. So 79.8 meters is a good final answer there. So that's our displacement. That's our acceleration. I'm going to do one more example with you here. Again, I encourage you to pause the video here, try it yourself. Unpause when you think you have an answer or you're stuck. So, in this question, what are we given? We're given, so it's a bullet leaving a rifle, and when the bullet leaves the rifle, it has a speed of 521 meters per second. So we're actually, pretend this is the barrel of a rifle, and we have the bullet inside the rifle. Just put a little golden bullet there. We're actually looking at the bullet accelerating inside of the muzzle. We're not worried of the rifle, sorry. We're not concerned after it leaves the rifle, just while it's inside. So basically, it leaves the muzzle, so the muzzle's the end of the rifle, right? This would be the muzzle here. It leaves with a velocity of 521 meters per second. So that's how fast it's going at the end, 521 meters per second. While accelerating through the barrel, the bullet moves a distance of 0.84 meters. So this distance of the barrel is 0.84 meters, right? That's the length of the barrel. We're looking for the acceleration. So essentially what we're given, so the distance traveled is 0.84 meters. The final velocity, right? The velocity at the end of its acceleration when it leaves the muzzle is 521 meters per second. And for all these questions, you might notice a little bit of a pattern. We need at least 3 pieces of information to find the 4th one, right? So what piece of information are we not given here? Well, I think a pretty good assumption is that the initial velocity of the bullet is probably going to be 0, right? It's starting from rest. So that sort of would make sense. So there we have our 3 pieces of information. We need to find the acceleration of the bullet. Just off the top of your head, you're probably going to, it's a bullet being fired out of a gun. It's probably going to be a pretty fast acceleration. Let's see if the calculations agree with that. Which equation can we use here? Well, if you look at what's missing from this, we don't actually care about delta t. We don't care about the time in this equation. When we don't care about time, it's going to be this equation that we use, right? It's a little bit of a complicated one. It's got all these squareds in it, but I think we're going to be okay. So to solve this, we're going to use the equation Vf squared equals Vi squared plus 2a delta d. Notice actually this is the only equation as well that doesn't have the little arrows above the v's and the a. And the reason is because when you square a vector like this, you're actually destroying some of the information. You're destroying some of the direction information. So it's not actually vectors when you calculate it using this equation. That's the only one that's like that because of the squared on the vector. Anyways, in order to solve this, let's again try to solve for a. Let's try to get a by itself. Before we do this, though, realize that vi is going to be 0. So this vi squared term just goes away. That makes our calculations a lot easier. This font is a little bit big here. That's okay. If I write here, it's going to be easier. So Vf is essentially, Vf squared is 2a delta d. So to solve for a, we can divide by 2 and delta d, right? That's going to cancel these out and cancel these out. And we have to do the same thing on this side. So 2 delta d. So to rewrite out that equation over here, a is just going to equal Vf squared over 2 delta d. Now we can just plug in our numbers. Our final velocity is 521 meters per second, and we're going to square that thing all over 2 times 0.84 meters. Okay. When we do this on a calculator, it'll come out to 521 squared. Don't forget to square it. Divided by 2 and 0.84. I get 161,572. And it's an acceleration, so we assume meters per second squared. Let's just double check that those units come out. If we sort of just off to the side think about the units here, on the top we're going to have meters squared per second squared, because that squared squares the units as well. And on the bottom we're going to have meters. And what's going to happen is that meters and that meters is going to cancel out. So yeah, we're left with meters per second squared. Perfect. So the answer here is in meters per second squared. So that's as we predicted, that's a very large acceleration. This bullet gets very fast, very quick. Now to look at significant digits. If we look at our original question, these two given values both have 3 significant digits, right? So let's round that to 3 significant digits. So that's going to be equal to approximately, the little dot is approximately, 162,000 meters per second squared. Or if you want to write it in scientific notation, 1.62 times 10 to the 5 meters per second squared. There we go. That's the answer. So what I'd encourage you to do now, I'm not going to do any more examples, but there are 3 more examples that you can try. If you want to check your answers, they are at the bottom of the page here, upside down, so you can check them as you go. All right?